Hello students, this is lesson U1A01b. Hopefully by the end of the period you should be able to say I can prove segments congruent. So I have not talked about this yet this year, and that is the foundations for this course, because everything has to be built from something, right? I know it's confusing for students to think of math as something that's really philosophical, but you know, math is actually the purest form of philosophy there is. And like any philosophy, we have to be base. We have to base our thoughts on some things, right? We have to base our truth on something. So there are these things called axioms. I want to spend like a couple minutes talking about this, and after we talk about these, we'll never like explicitly talk about them, but it will be implied in all of our understanding. And I would say four of the five things here are fairly obvious. So let's just take a look, okay? So what exactly are axioms? An axiom is actually a statement that is self-evident, okay? Meaning like we accept these as being true, okay, without having to go through any kind of rigorous proof. A lot of mathematics, when we proclaim something, we often have to provide supporting evidence, just like in any discipline. Okay, but math tends to be just to be more precise in their language. So what are these axioms? What are these statements that we find to be self-evident, to be true, without the need for it to be proven in any way, right? So the five axiom goes like this. The first one being that a straight line can pass through between any 2 points. We know that, okay? Again, we're using this as a basis for problem solving in the future. So again, the first axiom, a straight line goes through 2 points. Any line segment may be extended indefinitely. We know that already as well. If we have a line segment, we can extend it in either way, and it will go on forever and ever. Axiom number 3, all points on a circle is r distance away from the center. So if you have a circle, all the points on the circle to the center will be uniformly the same, and we refer to that length as the radius. And again, we know this walking into this course. Axiom number 4, all right angles are equal. That makes sense because all right angles equal to 90 degrees, and all 90-degree measures will equal to one another. These four axioms, fairly obvious, and we regard them as being true without having to go through any rigorous proof. The fifth one here is the one that I find that requires just a little more imagination, a little more visual thinking, and it does need to be reminded every now and then throughout the course. And that is, and I'm going to read this the way that it's read, and then I'll do a little bit of interpreting and translating. And that is, for any given point and on a given line, there is exactly one line through that point that does not meet the given line. What this is saying in translation, okay, even though this is written in English, it doesn't necessarily feel like it's English. So I have a given line here, and this line goes on forever, right? Because that's what a line is. It extends indefinitely in both ways. And then if I have a point, which is over here, and what happens is if there is another line that I can draw passing through that given point, such that this line will never ever meet the given line that's already that's present here. So how do you characterize that new line that's drawn? How do you characterize the second line that's drawn in comparison to the first line? Well, the adjective that we use, which is not put into this axiom, is that these two lines are referred to as parallel. So parallel lines will never ever meet. That's what this axiom is saying. So these five axioms, okay, these five facts that we find self-evident as factual and true, okay, is what we are going to build all of our knowledge from, okay, and then from this we can produce other things. However, these five facts require some logical manipulation. Okay, so we can't really just like build all of geometry from these 5 things. We need other logical reasoning, okay, to pair different axioms together and to build other things. So what are those logical statements called? Well, in geometry, in math, not just in geometry, we have these things called postulates. And a postulate is it's a logical statement. And again, this logical statement is regarded as true and does not require any proof. This is a postulate, okay? A theorem, on the other hand, a theorem is not a postulate. A theorem is also a logical statement. However, a theorem requires proof. So, so you know how in the previous lesson I went over this the segment addition postulate, where if I have a line segment and the line segment here is broken up into this into that manner there. The segments AB plus segment BC will make up the entire segment of AC. That right there is a logical statement, and this logical statement doesn't require any proof. We find this to be, again, self-evident and is accepted as true, and we use these postulates to then create other things, all right? So what exactly is a theorem then, right? Well, you've actually worked with theorems in the past. This is an example of a theorem. This is a very famous theorem. This is the Pythagorean Theorem. And this is not a postulate because this is not so obvious. This is, again, a logical statement. However, in order for people to use this, it does require some proof, okay? I'm not going to go into the proof of this right now, but recognize that this is an actual theorem. This is also another example of a theorem, which everyone here have used at one point or another. This is the quadratic formula. You may be asking yourself, like, wait, that's a formula. Now, how is that a theorem? Well, again, this formula and theorem moving forward are actually rather interchangeable. A formula can be considered a theorem because a formula is a logical statement, and this logical statement does need to be proven. Okay, so that's the distinction. If you hear me use the word postulate, that is because this is something that we regard as true and that does not require any proof. If I use the word theorem, that is a logical statement that requires some proof. All right, so moving forward. Segment addition postulate is the postulate that we will be needing to use for this lesson. There's one other idea that I want to briefly talk about, okay? Just because this is an idea that is riddled throughout my solutions. However, I've made some executive decisions. I'm not going to require you to distinguish the difference between congruence and equality. However, I do want to talk about it a little bit so that you're clear that there is some subtle difference. Okay, so this is the definition of congruence. What exactly is the definition of congruence? Well, it's set. Remember, in the other lesson, I told you two objects, okay, can be described as being congruent with one another, and the reason for that is we can say that the two objects can maybe superimposed one on top of the other, and it's going to be the same in every which way. We cannot add congruent things, but what we can do is we can add the values of those of the congruent objects. We can add their lengths, we can add their weights, we can add their areas, and so forth. So what this is saying, definition of congruence, segments, okay, is we're saying that segments that are congruent will therefore have equal length measures. And then the same thing could be said that segments that have equal length measures will therefore be congruent. Again, this concept is riddled throughout my solutions, but I'm not going to require you to express your solutions through the use of this concept here. Okay, just because, and the reason for that is this is not a concept that's heavily stressed upon in the region's exams. Actually, I've never seen them stress this in any kind of proof on the Regents exam, so I'm not going to force you guys to go through that, okay? All right, so let's get to our first example together. So what I have right now, okay, is a line segment, T-O-N-Y. Those are all points on the same line. They're all collinear. So Tony is a line. That's what this thing here is saying. Tony is a line. And I'm telling you that TO is equal to 3x. I am also telling you that ON is equal to 7. I'm telling you that segment TN and OY both have a length of 13. I'm telling you that NY has a segment has a length of x plus 4. And the task is to prove that these two segments are congruent to one another. Pause the video for a moment, see if you can convince yourself that this last statement is true. Convince yourself that this is that this makes sense to you. All right. So welcome back. What we're going to do, okay, is before you tackle any geometry problem, it is always important to just draw all over the diagram. So that's, I'm going to model for you, okay, how that will look like. So one more time, right now, we have the segment ON is equal to 7. I'm sorry, TN and OY is equal to 13. I'm going to start with that. So this overall segment here is 13. This overall segment is 13. So what I'm going to do is I'm going to say that this is 13 and this is 13. All right. And then we also recognize that segment ON is equal to 7. Segment ON is equal to 7. And we need to somehow prove that this statement here is equal to, is congruent to, TO is congruent to NY. Can you see why this is 100% the case? So let's think about this, right? If TN is 13 and ON is 7, one more time, I'm going to get rid of this. I'm going to get rid of this so that you can see it clearer. Whoops. All right, so again, Tn is equal to 7, and Tn is equal to 13, and On is equal to 7. So if that's the case, then what would make TO? TO would have to be definitely 6. And wait a minute, if On is equal to 13, right? If On is equal to 13, and OY is equal to 13, and On is equal to 7, what would make that of NY? Well, NY therefore also have to equal to 7. All right. So in order for me to go through this, I didn't say this. This is enough information for us to prove that those two things are congruent. There's one more thing I forgot. I left out here. We should show that x is equal to 2. Okay. Show that x is equal to 2. Okay. As part of our proof. So we're going to. I hope by now that this argument here makes sense, that TO does equal to NY, and that TO does equal to NY, and that this proof is possible. So let's take a look. All right, so in order for us to go through this, let's create that statement and reason chart. This is the format to which I want you to conduct your argument, to conduct the proof. So let's make the statement and reason chart. So the statement here, I'm going to write statement. And then this is the reason. Let's write down all the given information. And that is TONY is a straight line. That TO is equal to 3x. That ON is equal to 7. That TN is equal to OY, which is equal to 13, and NY is equal to x plus 4. All right. So I'm going to go and prove the first thing in this problem, which is to show that x is equal to 2. Okay. We're going to try and prove that x is equal to 2. So how is that possible? All of these things here, these are givens, by the way. Okay? So we're going to go through and try to prove y is x equal to 2. So how is that going to go? Well, if we go through the process, okay, of thinking about, well, again, what makes up Tn, okay? Tn is made up of To and On, isn't that right? So that's what I want to say here. I want to say that for statement number 6, Tn is equal to To plus On. What would be the reason for this? Oh yeah, that's right. That would be segment addition postulate. So recognizing that this is true, okay, because I'm given information about Tn, and I'm also given information about Oy, why don't I just go through and write that out for Oy as well? Oy is equal to On plus Oy. And again, for the same exact reason. So now that I know this, okay, now that I know this, my goal is to show that x is equal to 2. So if that's the case, well, wait a minute. Don't I have values for all of these things? Don't I have values for Tn, for To, and On, and all these things? I have values for all those, right? So what I'm going to do now is I'm going to perform a substitution then. So I'm going to perform a substitution, and I'm going to say, oh, really? For line number 8 and for line number 9, I'm going to perform the substitution. I want to say that Tn, which is equal to 13, is equal to To, which is equal to 3x, plus On, which is equal to 7. And I want to perform the same substitution for Oy, On, and Oy. I'm sorry, On and Ny, that should say here. All right, so Oy is also equal to 13, which is equal to On, which is 7, plus x plus 4. And what's the reason for this, you may ask? Well, this is because of substitution. So both of these lines are substitutions. However, for line number 8, I performed a substitution by substituting what values into where. So let's take a look. I substituted lines 2 and 3, 2, 3, and 4 into line 6. So I substituted line 2, 3, and 4 all into line 6. And then I'm going to do something really similar for substitution. I performed a substitution, and I am taking lines 3, 4, and 5 and placing that into line 7. All right, so now what has happened is this problem, which originally was a geometry problem, can you see now, at least for lines 8 and 9, it is looking more and more like an algebra problem. So, and our goal is to figure out what x is, right? Well, since both of these lines, lines 8 and line 9, okay, they both equal to 13, can I just then do this, right? Can I just say, oh, this is the same thing as 3x plus 7 is equal to 7 plus x plus 4, right? And again, this is because of substitution. And this is true because of substitution between lines 8 and into line 9, right? So I'm substituting one into the other, and this is what I get. And upon inspection, I can see now I have 7 on both sides. Let's try to get rid of that. Okay, if I subtract both sides by 7, right, I need to first say that 7 is equal to 7. And this is because of reflexive. And because I have 7 is equal to 7, I can then say, oh, I can subtract lines 10 and 11 together to get 3x is equal to x plus 4. And this is because of subtraction between 10 and 11. Lastly, I want to isolate x. So I want to subtract x from both sides. So I want to say x is equal to x. So from here, I'm going to subtract lines 12 and 13. So I'll end with 2x is equal to 4. So I'm going to subtract. And lastly, I'm going to divide both sides by 2. So this is, again, because of reflexive. And I'm going to divide both sides by 2, so x will equal to 2. So this is going to be division. L14 divided by L15. So we've proven the first thing that we were set out to do, which was to show that x is equal to 2. And then the second thing that we were set out to do was to show that TO is congruent to NY, right? All right, so let's do that. So TO is congruent to NY. So because I know that x is equal to 2, and our goal was to figure out what TO was, right? So TO, okay, is equal to 3x. Wasn't that right? So TO is equal to 3 times 2 then. So this is because of substitution between line 16, substituting that into line 2. So substitution line 16 into line 2. And we're going to perform a little bit of simplification. We're going to say that TO then is equal to 6, and this is because of multiplication. And then 19, what we're going to do is we're going to figure out what NY is. NY is x plus 4, right? So x is 2 plus 4. And then this is, again, substitution. And we're substituting information from line 16 into, let's see, let's go back up. Which line was that? That was line 5, into line 5. So therefore, NY after addition is also 6. Lastly, our goal was to show that TO is congruent to NY, right? Since TO is equal to 6 and NY is equal to 6, we know that TO and NY are actually equivalent to each other. We can therefore say TO is congruent to NY. And this is because, again, substitution. Again, if you look at my solutions to the problems that I give related to the assignment, related to this assignment, you're going to see I have definition of congruence riddled all throughout. Ignore that, okay? I need you to just make sure that you understand the overall logic, ignoring the steps that I had written out involving definition of congruence, okay? All right.